this talk is just to answer one single question. How do we actually quantify solute-solute selectivity? So hopefully I will answer this question, but I want to warn you that maybe at the end of the talk, you might find this even more confusing, which means that there are more questions to be asked. But anyway, let's get started. So I will try to be brief here. So solute-solute separation basically is a new direction where we try to not only just separate water from solid, but actually separate different solids within the feed water. So there are several motivations. This has been mentioned, I think, multiple times in previous talks. For example, resource extraction from brine, like lithium or rare earth metal, any strategically important elements, and a nutrient extraction from municipal wastewater and also industrial wastewater reuse. There are also some topics about, for example, carbon capture, where you use really strong base to absorb carbon dioxide, and then you want to separate the hydroxide ion and the carbonate. So there are many applications for solute-solute separation. And so the membrane, although there are many processes that can be used, for example, you can do precipitation or ion exchange or absorption, but membrane processes remains the most promising and actually most widely studied process for ion-ion separation. So there are a few papers here just in the past 2 years, just talking about like membrane processes for solute-solute separation. So basically there are two major processes. One is nanofiltration and also electrodialysis. A lot of people nowadays focus on nanofiltration because of its simplicity. And there was a really nice talk by my postdoc advisor, Manny Elimelech, 2-3 days ago about some fundamental insight in how to achieve better solute-solute selectivity using nanofiltration. So some ongoing developments for this topic. So a lot of polymeric membranes like polyamide membranes or other, for example, membranes using polymerization. And then there are also a lot of membranes using nanomaterial building blocks such as graphene or graphene oxide, MXene or MOF, biomimicking channels, aquaporin, etc. So the question I'm going to ask today is, how do we quantify solute-solute selectivity? Well, you may think if there's so many papers out there, of course, we are already very familiar with how to do this, right? So why this is even a question? So in an ideal scenario, you want to basically reject all the solids that you don't want and let all the solids that you want to pass through the membrane. But in reality, that's usually not the case, right? So you have a certain degree of passage for each of the salts, right? So in order to quantify the performance of the separation, we need to find a way or a theoretical framework to quantify the selectivity. In general, there are 3 different measurement methods. One is just filtration, right? Just like nanofiltration. I think all the audience are very familiar with this. And then a lot of the study are actually performed using a diffusion experiment, right? So basically this is diffusion of ions under the concentration gradient, and then electromigration, which is basically ion movement under the influence of an electric field. So I'll just maybe make a few comments on each of this. So filtration, basically nanofiltration experiments. So this is most practically relevant if the membrane is intended to be used for nanofiltration, or basically pressure-driven filtration for separating different solids. You can perform single salt experiment or mixed salt experiments using this setup. And then you can change the water flux and the feed concentration. And these variables may have impact on the solute-solute selectivity that you measure. And then the second class of measurement you can do is the concentration gradient-driven diffusion, or just diffusion in short. So these are basically diffusion experiments using a diffusion cell. They are, although it has been used in for many membranes, including like conventional polyamide membranes, but this was usually, I think the original intention for this was to be used for delicate membranes that cannot actually sustain any hydraulic pressure, right? For example, in the early days when people developed those graphene oxide stack membranes or even single layer graphene membranes, it's impossible that you can actually do nanofiltration experiment with those types of membrane unless you engineer a really robust support, which was not present at the time. So people use diffusion experiment to measure the ion flux, and from that they get the ion-ion selectivity. Again, with this setup, you can do single salt experiment or mixed salt experiment is your choice. And the variable is basically the feed concentration. So this is one a representative diffusion cell. So it can take different form factors, but this is one representative shape or form factor. So you have feed solution here, receiving solution here, and basically you just measure you can either measure the conductivity if you're trying to do a single species solid, or you have to take samples and then maybe do a chemical analysis in order to find out the composition if you are doing a mixed solid experiment. So an experimental data would usually look like this, right? Depending on the concentration and also the species, you will usually have a linear increase of the concentration in the receiving solution as a function of the diffusion time. From that, you can calculate the flux. The two caveats in performing this experiment. The first is osmosis. This is especially true when the concentration of the feed solution is relatively high. So this is basically the mechanism of forward osmosis, which I believe many of you are quite familiar with. So water would basically migrate across the membrane to try to dilute the feed solution, while our only intention was to actually have the ion moving across the membrane to the receiving solution. So one solution to this challenge or to this caveat is to do osmosis offset by basically putting some large solid that we know definitely would not be able to pass through the membrane. For example, some sugar molecule like sucrose, and to basically achieve the same osmotic pressure on each side so that there's no net water flux. So in this case, you can basically we can attribute the change in concentration solely to the solid flux from the left to the right. And then the second caveat in doing this experiment is the internal concentration polarization. Again, this is a concept people know a lot in forward osmosis. I'm not going to elaborate here because it would take some time. But the idea is that if you don't correct for this effect, basically what you measure, right, the solute flux and also the solute-solute selectivity would not only account for what is happening in the active layer, which is what we're mostly interested in, but also account for phenomenon that happens in the support layer and maybe even the boundary layer. So for example, the different diffusivity of different ions. So we need to account for this effect if we are interested in what is going on within the active layer. Okay, lastly, concentration gradient driven diffusion. So basically this is a linear sweep photometry experiment. So you just, you have an electrode placed across on the two sides of the membrane, and you apply a voltage. So there's current. Basically, you change the voltage pretty fast from negative to positive, and you measure the corresponding current, and then you basically can find out the conductance of the membrane, and relate that to the ion flux. So this is relevant to electrodialysis, but it also has been used a lot for membranes that are intended for nanofiltration because there's no way to measure it under pressure. So it's used for membranes that are not delicate and with a very small effective area. For example, there studies who's that investigate like nanoscale pore, right? So multiple nanoscale pore, which is not even a membrane. So it would take infinite time to actually measure the change in concentration in the receiving solution, which is not practical. So they use this kind of method, which is kind of like a more in situ measurement. But with this method, you can only measure single salt feed solution. You can't do mixed salt because all you measure is just the electric current. You can't distinguish the contribution between, like, for example, two different cations or two different anions. So it's only single salt measurement. The variable, again, is the feed concentration. So when you do this electromigration measurement, what you're really measuring is actually the total resistance. So what you want to do is that you want to do a reference measurement, or the measurement of the blank conductance by removing the membrane, and then you're going to subtract that conductance from or subtract that resistance from the total resistance to get the resistance of the membrane. So that's how you perform the experiments. Okay, so now we know the three different measurement methods. Let's look at the definition. The definition of selectivity in all cases is basically the ratio between the normalized the ratio between the feed concentration normalized flux of the two species. So we're not only comparing the flux of the two species, but also comparing the feed concentration to be more fair. So for filtration, for an NF experiment, this is actually equivalent to the ratio between 1 minus the rejection. So we measure the rejection rate, and we can calculate this selectivity. For diffusion experiment, because we measure the flux directly, so this is basically we just use the definition directly. While for electromigration experiment, it's slightly more complicated. Basically, we need to compare the concentration normalized conductance for the two different species. And then we also need to correct that using the transference number, which basically quantifies the contribution of the movement of a certain species to the total current. So this correction is usually not performed in many studies, which may be okay for some of them, but it will lead to large deviation for the others. Okay, so in this work, what we're going to do is we use these three methods to do some experiments with just like a commercial nanofiltration membrane. In this case, it's from Cinder. We want to see whether the results are actually comparable, and whether basically what factors would actually affect the selectivities. So we just measure this using three salts, sodium chloride, magnesium chloride, and sodium sulfate, so that we can actually compare the cation selectivity and the anion selectivity. In all cases, we use different feed concentration just to investigate the impact of concentration. So for nanofiltration, for the filtration experiment, we try different fluxes, and we also try single versus mixed salts. For diffusion experiment, we perform experiment with and without the osmosis offset, and we also did this using single and mixed salt. Finally, for the electromigration experiment, we can only do the single salt experiment, as I explained before. Okay, so now let's look at the result from single salt solutions. Not necessarily because it's relevant or is practically relevant, but because this would be the starting point. And in fact, these are actually it comprise most of what people have done in the literature, right? So a lot of the selectivity reported in literature was actually performed using single salt experiments. So this is from the filtration experiments. So as you can see here, these are the rejection for the sulfate salt, like the magnesium salt, which are close to 100%. And then as you increase the concentration, the sodium chloride rejection would go down. So the selectivity based on the definition would look like that. So in general, the selectivity would increase with increasing feed concentration, except at this relatively high concentration range. So this actually raised another issue or another question regarding the definition of selectivity, which I do not have time to get into today. But basically, the problem or the reason why this occurs is that selectivity, based on the current definition, which every single person adopts in the community, is extremely sensitive to the rejection of the species that is highly rejected. but much less sensitive to the species that is less rejected. So I'm not sure that's actually a good definition, but that would belong to another conversation. Okay, and then we also look at the impact of permeate flux. So there's not really a clear trend here, and the values do not really vary that much at different flux. So our conclusion is that selectivity is weakly dependent on water flux. Again, these are still single salt experiments. And then we look at diffusion experiments, basically with the diffusion cell with and without osmosis offset. So with osmosis offset, these are the solid lines here. So this is the flux as a function of concentration. And then the dashed line, the dash curves without offset. So basically you have osmosis occurring, water osmosis occurring in this dashed line experiments. So the selectivity based on these two sets of experiments are summarized here, both for cation selectivity and the anion selectivity. The general conclusion is that osmosis has a big impact in selectivity. If you don't correct for that, for example, in this case, when you have a relatively high concentration for anion selectivity, the values for selectivity can vary by almost 2 orders of magnitude. And also selectivity in general increase with increasing feed concentration. Lastly, electromigration. So these are the conductance, the corrected conductance as a function of concentration for the 3 different salts. And this are the calculated selectivities for the cation groups, the pair, and the anion pairs. So there's no clear dependence of the selectivity on feed concentration based on the electromigration experiments. Now, if we want to compare the 3 methods, right? So here we have a figure showing the solute permeability. So this is the permeability through the active layer. Basically, we correct for example, for diffusion experiment, we correct for the effect of concentration polarization, both internal or external. And so this is basically the intrinsic permeability that we estimated to the best we can. So as you can see here, we measure the permeability for the different salts for filtration and diffusion. But for electromigration, we can actually decouple the contribution and find out the solute permeability for the individual species. And based on this, we can calculate their selectivity. So here, the open or the empty bars are for the intrinsic selectivity based on the permeability through the active layer, while the dash bars are for the apparent selectivity, basically without correcting like concentration polarization. So as you can see here, the intrinsic selectivity is always larger than the apparent selectivity, and the selectivity differs between different methods. In this specific case, filtration methods actually use the highest selectivity, while electromigration use the lowest selectivity for this specific study. Now let's get to the mixed salt selectivity, right? So mixed salt selectivity is much more practically relevant as compared to single salt. So our idea is our intention is to see whether they are actually comparable. So these are experiments with mixed salts and single salt. So the solid lines are for mixed salt and the dashed lines are for single salt. These are the rejection as a function of concentration. So as you can see here, the concentration has a clear effect on the mixed salt selectivity, which is in dash bar here. But relatively small impact on the single salt selectivity. So there's no clear trend for a single salt selectivity. And then this is for the diffusion experiment. Again, similar to what we have seen in the last slide. And I mean, in terms of the definitions of or the description of the both figures. But here, what we observed was that concentration has a weak impact on the mixture selectivity in diffusion, which is different from the filtration experiment. And we suspect that this has something to do with the effective contribution in filtration. but this is not, we're not certain about that. So this is worth further investigation. Okay, so if you compare both methods, you will see that mixture selectivity is more dependent in filtration than in diffusion. I mean, more dependent on concentration, feed concentration in filtration than in diffusion, and then it's much higher in filtration than in diffusion. If the concentration, especially when you have a high concentration of the feed solution. Okay, so the conclusion here is that the solute-solute selectivity is relatively independent of flux in filtration, so which is good. It means that no matter what flux you use, the data should be comparable between different experiments. Now, unfortunately, the solute-solute selectivity differs between measurements using single salt and mixed salt. So as I said, a lot of the study were actually performed using single salt experiments, and it would not be the same in mixed salt experiment, right? In mixed salt experiment, you have other phenomenon or mechanisms that are playing a role here. For example, you have the Donan equilibrium, which can actually lead to the negative rejection of some solids, which is impossible in single salt experiments, right? So the two are very different in most cases. And it also differs very much between different methods. So by different methods, I mean the three classes of measurements we just talked about. So, and it also has a different concentration dependence for different methods, right? So with filtration, it's strongly dependent on concentration, not as much for the diffusion experiment. So these are the conclusion. It's not like the conclusion is not very, very the conclusion is not very appeasing, let's put it this way, right? So this is not something we want, right? We want something that would make us feel very comfortable when we actually compare like results from different studies and different experiments. But that's really not the case, right? So, and some thoughts based on this conclusion. So if you look at a lot of papers, you will see plots like that, right? Let's say this is the selectivity between X species and Y species, and then this is some kinds of permeability, either water permeability or a permeability of a certain salt. And then the literature data is here, and then our work is here, right? So people like to use this a lot to show basically the excellence, the outstanding performance of the membranes. Now, but based on this study, it seems like this work, I refer to this as this work plot, should be interpreted with extra caution, especially for solute-solute selectivity, because a lot of these data are actually measured using different measurement methods, right? Some are mixed salt, some are single salt, and different conditions. So inherently, they are not actually comparable, right? So it is possible that a membrane here can perform better than this one if it's measured in the same condition as this one, right? So we have to be really, really careful in trying to interpret this kind of data. Whenever, so, and just a few suggestions, whenever possible, selectivity should be measured using NF or ED, basically what you intend to use the membrane for, and with mixed salt feed solution for the purpose of being relevant. And lastly, for membrane development research, right, if you don't have a very clear goal about what this membrane is, like, for example, you don't know what this membrane is going to be used for in terms of the specific feed water composition, right? So for like in some study, more applied study, you know the exact feed composition of the salt lake, that's totally fine. Just use that for relevance. But without that like specific application, maybe we need a unified testing framework so that everyone just follow that framework so that the results are actually comparable. And I think this is very much in need going forward if we want to have basically a community where we can develop membranes that can compare with each other. So with that, I want to thank you for your attention. Oh, there's one more here. So yeah, I just mentioned that. So for research with clear target application, the composition should be determined by that application. Otherwise, we really need a unified framework throughout the community. Okay, so this work was performed by Yu Wang, which was a very capable PhD student of mine, and Jinwei Zhang was an undergraduate student in the University of Hong Kong, and now a master's student in Berkeley. And then our collaborator, Professor Chu Yang Tang from the University of Hong Kong. I would like to acknowledge the funding agency as well. So with that, thank you very much, and I would love to take any question if you have.
Thank you, Sihong. It was really interesting topic, and you know, during the plenary speak of many, we mentioned this problem. So you now give us a very good answer. Here we got a few questions. I have a few, but I will ask you later. So the first question is that in general, when we use monovalent membrane, we can get selectivity in electrodialysis. However, monovalent anion selective membrane is less selective than monovalent cation exchange membrane. Why?
I'm not sure about that. So this is, I just don't know. Yeah, so this is not.
That was a quick answer. But anyhow, that's a good question as well. The second question, you need NF membrane tests. I'm wondering what might happen with RO membrane.
Okay, so we didn't use RO membrane because RO membrane, if a good one, good RO membrane would reject practically everything. So, and that would not give us the selectivity. So that's why we here choose an NF membrane. We work with this. We work with several different NF membrane, and this membrane is particularly good in rejecting any kind of divalent ion, like regardless of cation or anion, and it has a reasonably low rejection of like monovalent ion. So this is why we choose this membrane, just to show the contrast between the divalent and the monovalent. Right. Which is not very common, actually. Not very common. You will see a lot of commercial membrane. They have really good rejection for, like, for example, sulfate, but then they have poor rejection for magnesium chloride. So you really need uniform pore size to be able to reject both sodium sulfate and magnesium chloride. And this specific membrane works pretty well.
Okay. The next question: do you have any suggestion for unified testing framework development?
Well, so we're writing this paper in the revision process. So we actually propose something, but I have to admit that it's completely random. So basically, there's no rationale behind it, right? Basically, well, maybe we need to give a little more thought into that. But basically, we should just propose something that everyone agree to, and then from then on, everyone just follow that protocol, so that the results are actually comparable. But whether we have a very strong rationale of choosing a certain like condition or certain method, I don't know. So and obviously there's some membranes that just cannot be used in pressurized filtration. For example, some very fancy nanomaterial membrane that can use only in a very, like, fabricated in a very small scale and cannot withstand pressure. So in theory, we can't really compare results from those to like what you measure using pressurized nanofiltration. I think there's more work need to be done here. Hopefully in future, we would have a theoretical framework that can actually relate results from one experiment to result in another experiment, right? So if this fancy membrane that cannot be scaled up for the moment would eventually be scaled up, can we actually predict its performance in pressurized nanofiltration? I think this would be a very interesting question to answer and would be very, very useful. But for the moment, this is just too complicated. And we thought about this, but we don't have a good answer yet.
Okay, we have two more questions because this is a very interesting topic. I give extra time for this keynote talk from Sihong. Product purity is key to achieving solute-solute separations. How do different selective equations explain the purity?
Oh, product purity. Okay, that's a really good question. So product purity, right? So this goes back to what I just mentioned here. So there's, I mean, if time permits, for another talk, which means I'm not going to do that. I think it would take a thorough discussion about whether the current definition of selectivity is actually meaningful. Because, for example, if you look at these two separation here, right, I think for most application, we will actually prefer this one, right, where you have slightly less rejection of this species, but much less rejection of what you want to pass through, right? So here the purity is much higher, I would argue. But if you just look at selectivity, like as it's defined now, then this actually gives you a much higher selectivity. And that is because if you look at the definition of selectivity, which is based on this equation, right? So this equation is equivalent to this equation here, which is everyone use, right? Everyone has adopt this definition. So if this is very high, let's say 99%, now if you increase that to 99.5%, it would have a huge impact on this value, while this one would not have a large impact on the selectivity. So in the end, whether this is a good definition is actually a good question to ask. So maybe we don't want a ratio. Maybe we just want a difference for some application. It also depends on what you really want to achieve in solid-solid separation. Whether you want the product to be rejected or you want those like the solid that are passing through, right? That would depend on your specific application. So that's a really good question. And this is something we are also thinking about, but we don't have a definite answer yet.
Sometimes purity is better with lower rejection. Yes, I agree. I think we don't have much time now. We will end this keynote talk from Sihong. If you have any more questions, you can send a message to Sihong. I think he will answer you tomorrow morning.
Yeah, definitely.
Good night, Sihong.
All right.
See you next time.
All right.
Thank you.
Good afternoon. Bye-bye.